All right, welcome everyone. So just a few reminders as we're getting started today. For people that have Thursday recitation, you'll have your recitation exam 2 today. So I sent the link for the Zoom meeting out this morning, so just be aware that you'll have your second exam today for the people in Thursday recitation. Also today, homework for learning outcome D1. What we did last week is due tonight, so make sure you finish that up. And we're on Tuesday we assigned homework for D2, and we're going to finish up D3 today. All right, so where did we leave off last time? We left off talking about the chain rule. And this was a derivative rule that allows us to calculate the derivative of composite functions. So where we have an outer function and an inner function. We have one function plugged inside of another. And so the process, what this rule says, is that the derivative of that composition is equal to the derivative of the outer function with the inner function plugged in times the derivative of the inner function. And we're going to see a few special cases of this chain rule depending on what the outer function actually is. And that's what we're going to look at next. So let's go to our first special case. And we're going to call this one the general power rule. And it tells us what to do if the outer function is a power. So something raised to the power r. Tells us how to handle that composition. And so we've already seen our basic power rule, which tells us how to differentiate things like, I don't know, maybe like if we wanted to differentiate x to the power 8, it tells us how to differentiate basic power functions like that. But the example we're going to look at, x to the 4 plus 9x plus 3 all raised to the power 8 is a little bit different. So if we compare these two, both of these functions, they both involve the same power function. So we have this raised to the power 8 over here, and then we also have this raised to the power 8 over here. So both of these functions seemingly involve the same power, raised to the power 8. The only thing here is that in this function, we have some extra stuff inside the parentheses. We have some additional x terms. So we're seeing here some extra terms inside the raised to the 8 function. And so in order to differentiate something like that, we're going to use really a special case of the chain rule. We call it the general power rule. So let's read through what this says. It says, let u be any differentiable function, then the derivative of u of x all raised to the power r is equal to r times u of x, all raised to the r minus 1 power, times the derivative of u. So we can see kind of elements of the chain rule there. So when we look at this r times u of x raised to the r minus 1, this part is similar looking to just our basic power rule. And so we kind of go through the same steps. In order to actually implement this general power rule, we really go through the same steps. So what do? Well, we bring down the power r. So we bring down our old exponent. We keep the term inside the parentheses exactly the same. So we look, see what's inside the parentheses, we just keep it exactly the same. And then we subtract 1 from the exponent, just like we would normally do with the power rule. So that part's really should feel pretty similar to our original power rule. We bring down the exponent, put it in front, keep what's inside the parentheses the same, and then subtract 1 in our exponent to get our new power. All right, so what do we do? What's sort of new here with the chain rule? Well, it's this extra thing that we're multiplying by here, this u prime of x. And so this is sort of this is really where the chain rule is coming in. The last part of this is that we multiply by the derivative of what's inside the parentheses. So that r times u of x raised to the r minus 1, that's the derivative of our outer function. And then the u prime of x that we're multiplying by at the end, that's the derivative of the inner function. And that's sort of the new part here. So let's see how this would work with our function h of x equal to x to the power 4 plus 9x plus 3 all raised to the power 8. We want to do the derivative. We see that it's a power function with some additional terms inside the parentheses. So we're going to use this power rule, this general power rule. So we bring down the power 8, keep everything in the parentheses exactly the same. So x to the power 4 plus 9x plus 3, keep it all the same. Subtract what we had in the exponent. So subtract 1 brings us down to power 7. And then we take those terms that are inside the parentheses and we multiply by their derivative. So we're going to do the derivative of x to the power 4 plus 9x plus 3. All right, so let's differentiate that. We keep going. So what's the derivative of x to the power 4? Well, that's 4x cubed. And then what's the derivative of 9x? Just 9. And then what's the derivative of 3? Just 0. So there's our derivative. Derivative of the power function part plus times the derivative of the inner function part. All right. So that's what we do if that's really a special case. This is really just the chain rule, but it helps to kind of break these apart into, what is your outer function. So this is what we do when we have the outer function as a power. Let's see what happens next when our outer function is trig. So again, we have a very similar rule. Maybe we call it the general trigonometric rule, but it reads very similar. So let u be any differentiable function, then, and this is specific for sine, the derivative of sine of u of x is equal to cosine of u of x times u prime. So we have a whole bunch of trig functions there. So there's like a specific rule for each of those. The one we've stated is just particularly for sine. So here, our outer function is sine of u, or sine of whatever. But we have a whole bunch of other trig functions, so similar rules would apply for them. But what does the chain rule process look like when our outer function is trig? Well, what do? We start by just differentiating our trig function. So derivative of sine is cosine. We keep the term inside the parentheses exactly the same. So we're just going to plug in u of x. We really just keep it the same. And then what's the last part? Multiply by the derivative of the inner function. So all of these chain rules, the last thing is you just multiply by the derivative of those terms inside. So what would be an example of something like this? Well, if we wanted to differentiate the function sine of x to the power 4 plus 9x plus 3, if we look at that, sine is on the outside, we have a big set of parentheses, and then there's some x terms inside those parentheses. So that's an indication that we're going to use chain rule. So how does the derivative work? Well, we differentiate sine. So derivative of sine, if we look it up, what's the derivative of sine? It's cosine. We have our big set of parentheses, and then we just keep the inner function exactly the same. So it's just x to the power 4 plus 9x plus 3. And then we take that inner function, the x to the 4 plus 9x plus 3, and we multiply by its derivative. And, same inner function as last time, so we already did that one. So we get that our derivative here is cosine of x to the 4 plus 9x plus 3. We're done with that, so that stays as is. And then if we differentiate, we get 4x cubed plus 9 for our derivative of our inner function. So that's how the chain rule works if our outer function is trig, or even inverse trig, same idea. So yeah, if we're looking at the chart, I have the list of elementary forms here. You should really work on getting these memorized for our elementary derivatives. It's just going to make things that much easier for you as we go forward in the course. So, I'm referring back to them now, but eventually we'll get to the point where it's just kind of expected that we have these memorized. All right, so, well, that was trig functions and inverse trig functions, what happens if with chain rule. We've also looked at exponential functions. So here's the case where our outer function is e raised to some stuff. So our outer function is an exponential. And again, this is just a special case of the chain rule. So it reads very similar. Let u be any differentiable function, then the derivative of e raised to the power u of x is equal to e raised to the power u of x times u prime of x. So when we look at this, it doesn't look like much is happening here, but we're using the chain rule, and the reason why nothing looks like or not too much is happening is because the derivative of e to the x is just e to the x. So this, in our formula here, this e to the u of x, this is really just the derivative, or we've really differentiated our outer function here. But because it's an exponential, it stays basically the same. So derivative of e to the x is e to the x. So differentiating the outer function, it's just going to stay the same. And then all that's new is this multiplication by u prime at the end. And that's what we come to expect with the chain rule, is we differentiate our outer function, and then we multiply that result by the derivative of the inner function. So we're going to multiply by the derivative of the terms in the exponent. So we see e raised to some stuff. We see a whole bunch of x terms there in the exponent. That's an indication that we're going to use chain rule. And so how it works is the derivative h prime of x. We keep our exponential part exactly the same. So it stays, it doesn't change. It's e to the x to the 4 plus 9x plus 3. That part stays exactly the same. Then we take those terms that are in the exponent, x to the 4th plus 9x plus 3, and we multiply by their derivative. So it's derivative of outer function times the derivative of the inner function. And then we've done this one before, so we just keep going until we're done with all the necessary differentiation. So x to the 4th plus 9x plus 3, when we differentiate, it's what we've seen, 4x cubed plus 9. All right, so that's our process for where our outer function is exponential. And we have a kind of even more of a special case, one that's very similar, where you'll probably see it enough where you might just have this one memorized eventually. So this is even more of a special case where k is just a constant here. So we have the function e raised to the kx. And let's see what this derivative is. So we're going to apply the chain rule. So let's say we wanted to differentiate e to the kx. So the derivative, the outer function is exponential. So we keep the exponential part exactly the same. And then we take the term in the exponent, we multiply by its derivative. So the kx is our exponent term. We multiply by the derivative of kx. And the derivative of kx, k is just a constant, so the derivative of that is just k. And that's exactly what we're seeing up here. Derivative of e to the kx is just k times e to the kx. And normally it's helpful to move that constant term in front of the exponential just to make it, just so you don't forget about it, or it doesn't, as you're writing things out, it doesn't magically work its way up into the exponent. So I like to put that constant in front. So write it as k e to the kx. All right, so that's when our outer function is exponential. One other special case that we're going to consider is with log functions. And the process is, again, these are all just special cases of the chain rule, so they're going to feel very similar. It's just that first part, differentiating the outer function, is going to be slightly different. So for our example here, our outer function is going to be the natural log of some stuff. So we call this the general log rule, but it's really just a special case of the chain rule. So let u be any differentiable function, then the derivative of the natural log of u of x is equal to 1 over u of x times u prime of x. And so when we look at this, our outer function is the natural log of some terms. And really the way to implement this derivative is kind of the first step here is to do the reciprocal of the inner function. So the first part there is just do the reciprocal. Our inner function's u of x, just have the reciprocal there, 1 over u of x. And why do we do that? Well, if we look at the natural log function, what is the derivative of just natural log x? Well, it's the reciprocal of x, 1 over x. So the derivative of natural log kind of is doing a reciprocal almost. And we keep the term inside the natural log function. We keep that as u of x, and then we multiply by the derivative of the terms inside the natural log function. So again, we're multiplying by the derivative of our inner function. So again, why is this kind of involving a reciprocal? Well, when we look at natural log, just natural log of x, and we do the derivative of that, it's just 1 over x. And so for this particular case of ln x differentiating to 1 over x, it's really the reciprocal of the input. So that's kind of what the derivative process is doing with natural log. So let's try an example here to see what's happening. So similar function that we've been looking at, but now we're going to see natural log of x to the power 4 plus 9x plus 3. So how does the derivative process work here? Well, we take that inner function, keep it exactly the same, and just flip it. So it'll be 1 over x to the 4th plus 9x plus 3. So that's the reciprocal of our inner function. Then we take our inner function, just as we've been doing with all the other special cases here, and we multiply by its derivative. So that's the heavy lifting. That's the chain rule. And then we just keep going. So we've done this one before. We get 4x cubed plus 9. So we're done differentiating. And usually it's helpful to just take that term and move it to the numerator. So just kind of do the multiplication a little bit there. So it's usually helpful to rewrite this as 4x cubed plus 9, put it on top, over x to the 4th plus 9x plus 3. So that's how we implement, or an example of how we implement the general log rule. All right, so that's really all the different rules we're going to be looking at. So let's just practice some more examples just to see, be able to identify what's our outer function, what's our inner function, and what's the general process that we're going to use. So let's look at first the function secant cubed x, or secant x cubed. So really that's what this function is. A lot of times the way we indicate notationally a trig function raised to a power is we put the power right on the trig function part. But really what this means secant x cubed. So if we look at this, really what's happening outside is our outer function here is this raised to the power 3. It's a power function. So that's what's happening outside of the parentheses. And then inside the parentheses is our secant x function. So that's our inner function. So what we're going to use here to differentiate this is our general power rule. All right, so let's see it in action. We're going to do h prime So how does the general power rule work? Very similar to our original power rule. So we bring down the exponent, which in this case is 3, put it in front, keep everything inside the parentheses exactly the same. So we'll keep it as secant x. Subtract 1 in the exponent, so that brings us down to a power of 2. And then we take the term that's inside the parentheses and we multiply by its derivative. And then derivative of secant x, in case we don't remember, what is it? It's just secant times tan. So we get 3 times secant squared x. We're done with that part. No more differentiating there. And then we only have to differentiate that inner function, and we said it was derivative of secant was secant times tan. And then maybe we clean it up. So we have 3 secant x terms that we're multiplying together there. So we can simplify that to just 3 times secant cubed x times tan x. And that's our derivative. So again, derivative of the power function times derivative of the inner function. All right, let's try another one of these. So something that looks very similar, but the process is going to be slightly different because our outer function is different, and that's y equal to secant of x cubed. So when we look at this, our outer function, it's the thing outside of the parentheses, and our outer function is secant. So we're going to use our general trig rule to differentiate this. So our outer function is a trig function, so we're going to use our general trig rule. All right, so what does that say? Well, it's going to tell us how to get y prime, our derivative. And we already know the derivative of secant. So it's secant times tan. And we're going to leave the variable part there blank for just a second. So we're just, for right now, derivative of the outer function, derivative of secant is secant times tan. And then into those parentheses, we're going to keep our inner function exactly the same. So our inner function was x cubed, so it goes in those parentheses. So what we did here, this is the derivative of the outer function. So the derivative of secant with the inner function kept the same and plugged in. So derivative of secant is secant times tan. Our inner function was x cubed, so that's where the x cubed is going into, if we look at our formula here, the x cubed is going wherever we see a variable. All right, so that's the derivative of our outer function part. That's not the full story. Then we take our inner function and we multiply by its derivative. So our inner function here was just the x cubed. And so if we do finish our differentiating, we get secant x cubed times tan x cubed. That part stays the same. We were done with that. And then the derivative of x cubed is 3x squared. And it would probably make it a little bit more readable, more legible, if we were to take this 3x squared. Again, it's not absolutely necessary. We're done differentiating, so for right now we could just stop there. But it'll probably make it a little nicer to take that 3x squared and move it in front of the secant if we wanted to rewrite that just a little bit further. All right, so a little more practice there with our chain rules. Let's try a few more. So let's look at the example 5 over the cube root of x squared plus x plus 1. We want to differentiate this. And sort of like we've seen with power functions in the past, we generally want to rewrite any root signs that we see as raised to the power 1 over n. So that's the first thing we're going to do, is instead of having that cube root, we're going to write this as 5 over x squared plus x plus 1, all raised to the power 1 over 3. That's just our standard technique for dealing with root functions. Now, as it's written, we have a fraction. So we might start thinking we have to use quotient rule, but there's no variable in the top. It's just a number. So another strategy that we've had is to rewrite a fraction with a negative exponent. So let's make that 1/3. We're going to get rid of the fraction and we're going to make it into a negative exponent. So we'll go one step further and write this as 5 times x squared plus x plus 1, all raised to the negative 1/3 power. And that's good. That's about as good as we're going to rewrite this function. And it's nice because we see that we have a power function ultimately here. So it's some x terms raised to the power, raised to a power. And so we can use our general power rule. So we're going to do y prime. And that 5 is a constant multiple, so nothing's really going to happen with the 5. It just stays in front. And really all the action is going to happen to just this power function part. So what are we going to do? We bring down the exponent, put it in front, or put it with the 5 there. So we'll bring down the negative 1/3, put it in front. Keep everything inside the parentheses exactly the same. So x squared plus x plus 1. Keep all that exactly the same. And then we're going to subtract 1 from the exponent. So we're going to get negative 4/3. So we have negative 1/3 there originally. We're going to subtract 1, get a common denominator. Negative 3 over 3 gives us minus 4 over 3. Just to kind of see where that negative 4/3 is coming from. So we've done the power rule part. That's not the end. Then we take our inner function, x squared plus x plus 1. We multiply by its derivative. And we're almost there. We just need to go a little bit further and finish differentiating. So when we do that, let's clean up the numbers in front. The 5 times the negative 1/3, we'll multiply those together. So we'll write that as negative 5/3. The x squared plus x plus 1 raised to the minus 4/3, we're done with that. So just keep writing it, but we're done with that. And really the only thing left to do is to differentiate the x squared plus x plus 1. And when we differentiate, we get 2x plus 1. So the derivative of x squared is 2x, derivative of x is just 1, and then the derivative of that 1 term by itself is just 0. And there's our derivative. So we use the general power rule to calculate it. Let's try another example. 5 times natural log of square root x. And same idea. We want to rewrite this first. We see a root function, so it's going to be helpful to rewrite that root function. Instead of square root x, we'll write it as x to the 1/2. So rewriting this, we get 5 times the natural log of x to the power 1/2. And we see parentheses, and inside those parentheses is x to the 1/2. So that's going to be our inner function, and then everything outside is our outer function. So when we calculate f prime of x, Oops. We're really, when we look at this, that 5 is just a constant multiple. So we really just focus our attention on the natural log, the variable part there. The 5 is a constant multiple, so we can go outside of the derivative process. So we just focus in on the natural log of x to the 1/2 and worrying about differentiating that. And we're going to use our general log rule for this. Really just a chain rule, but specifically the general log rule. And what does it say? Well, the 5 is out front, so we'll just keep writing it. And then for our general log rule, we take what's inside the log function and we multiply by its, and we do the reciprocal of it. So we're going to have 1 over x to the 1/2. So we take what's inside the natural log function, we just do the reciprocal. Now that's not the end of it. We take the inner function and we multiply by its derivative. So the 5 was a constant multiple, it just stays in front. Then the derivative of our outer function was like that reciprocal, 1 over x to the 1/2. And then we multiply by the derivative of our inner function. And if we differentiate, bring down the 1/2, keep our variable the same, x, and then subtract 1 from the exponent. So we get x to the negative 1/2. And then if we clean this up, there's a little bit we can do. I would move the 5 and multiply that with the 1/2, so get all the constant terms together. So I would write this as 5 over 2. Then we have x to the 1/2. And then maybe it's helpful to rewrite that negative exponent rewrite it as a fraction instead. So that other term is going to become 1 over x to the 1/2. And then we see that we can multiply those together. So we have 1 over x to the 1/2 times 1 over x to the 1/2. And when we multiply those, we add the exponents. So we get 5/2 times 1 over x. And that's pretty good. Maybe we'll stop there with that one. So just general log rule. What happens when the outer function is a log? All right. Practice, practice, practice. Let's try a couple more. So chain rule, this is something we're not going to get away from. So, it's good to do a bunch of examples just because basically for the rest of this course, rest of Calc 2, if you go into Calc 3, there's chain rule all along the way. So we're not going to be able to escape the chain rule. So this is definitely a technique that you want to practice over and over again. All right, so let's try a couple involving inverse trig functions. See how that works. So in the first one here, we're going to differentiate 1 over the inverse sine function. So just to be careful here, that -1 that we're seeing is not an exponent. It's telling us that this is the inverse sine function. But we have a fraction here, and the numerator does not have a variable. So our technique for this is to rewrite this with a negative exponent. So this is going to get a little, the notation for inverse functions gets a little messy when we talk about powers. So we're going to rewrite this as inverse sine function, all raised to the -1 power. So I kind of like to write the -1 on that sign. I like to write it a little bit smaller just to remind myself that it's not actually an exponent. It's just telling us it's the inverse sine function. And then I write a nice big -1 outside the parentheses saying, yeah, this is a power function. It's the arc sine function raised to the -1 that we have. So again, this -1 is an exponent. This -1 is not an exponent. That's just telling us it's the inverse sine function. So sometimes it's a little bit helpful to, if you wanted to, we could rewrite this as instead arc sine of x all raised to the -1. Really just so we don't have that confusion in terms of which -1 is the exponent, which one's not. So, you know, it's entirely up to you if you want to just convert it to arc sine. And the notation is, you know, we kind of use both. So it's both versions are kind of helpful, have their benefits. But in terms of dealing with power functions, it's probably a little bit easier to rewrite this as just arc sine of x, just so you don't mess it up. All right, so let's see what happens then when we apply our chain rule to calculating this derivative. And what we see here is that the outer function is a power function. It's raised to the -1. So when we differentiate it, we're just going to use our general power rule. So let's see what that looks like. We bring down the exponent, which was -1. Keep everything inside the parentheses exactly the same. So let's rewrite this as arc sine of x. Keep that exactly the same. And then we subtract 1 in the exponent. So we go from -1 down to -2. And then we take those terms inside the parentheses, the arc sine of x in this case, and we multiply by its derivative. And so this is where we need to know that the derivative of the inverse sine function is, what is it? It's this 1 over square root 1 minus x squared. So we just keep going. And it's 1 over square root 1 minus x squared. All right, so there was just an example involving an inverse trig function, but really most of the new stuff there was just by applying the general power rule. Let's see an example, though, where the outer function is an inverse trig function. So that's the next one, arctan of 3 of x. And now we don't have that messy -1 exponent. Again, not exponent, that -1 notation. Again, that -1 notation does have its benefits, as we'll see in a little, in a few lectures. That does have its benefits, but it does get a little bit messy when we're talking about exponents. So arctan is a kind of a nice version of our inverse tan function here, notationally. And what we're going to do is our outer function is arctan, and our inner function is this 3x. It's inside the parentheses. So when we differentiate this, how is it going to work? We're going to calculate y prime. What's the derivative of arctan, or inverse tan? We go to our table here. Derivative of inverse tan is 1 over 1 plus x squared. So we're going to write that in, 1 over 1 plus, and then instead of writing x squared, we're going to leave it kind of just a blank set of parentheses there. So we're going to just write that as 1 over 1 plus blank squared. And inside that blank, we're going to fill in our inner function, which is 3x. So this is really the derivative. What we just did here is the derivative of arctan with our inner function plugged in. So we do the derivative of our inverse trig function, and we keep our inner function the same. So derivative of arctan is 1 over 1 plus something squared, and that something is our 3x. So that first part of our chain rule here is 1 over 1 plus 3x squared. Then we take our inner function, which was 3x, and we multiply by its derivative. And then we just keep going. So that fraction 1 over 1 plus, we'll write that as 9x squared, so we'll actually do the multiplication. And just a reminder, the squared would distribute to both the 3 and the x because it's multiplication. And then we differentiate 3x and we get 3. And it's probably helpful to just kind of consolidate all of that into one fraction. So write this as 3 over 1 plus 9x squared. All right. So those are just some good examples for how the chain rule works in practice. Now, why does it get the name chain rule? Well, as we're going to see next, is because you can do it more than once. So a lot of times there's functions inside of functions inside of functions, and so you just kind of work your way through all the different layers of your function, and just kind of you produce one link in the chain. You just keep going through. So that's what we're going to see in this next example. Is we're going to differentiate the function sine of cosine of natural log x. So let's start it off. We're going to calculate f prime. And when we look at this, sine is our outer function, and cosine of natural log x is our inner function. So the very last thing we do is the sine, and then everything else inside the parentheses is cosine of natural log x. So when we apply our chain rule, we differentiate the sine function, we get cosine, and we keep everything inside the parentheses exactly the same. So what was it? It was cosine of natural log. We keep all that the same. Then we take those inside terms, the cosine natural log x, and we multiply by their derivative. So we did the derivative of our outer function sine, kept everything plugged in exactly the same, and then multiplied by the derivative of our inner function. And so that's the first time we use chain rule. And we're actually going to use it again. And I'm going to write this a little bit nicer. So we have cosine of natural log x. And we want to do the derivative of this now. And so when we look at this, if we just consider that, cosine is an outer function, and natural log x is the inner function. So when we just focus in on doing the derivative of cosine natural log x, we have to use a second instance of chain rule. So we're going to do it again. So this first part stays the same. We're done with all of this. So cosine of natural log x. We're done with that part. Then we do the chain rule again. So derivative of cosine, we look it up on our table there. It's negative sine. And we keep everything inside, we keep our inner function exactly the same. So it'll be negative sine of natural log x. And then we take that new inner function and we multiply by its derivative. So just imagine this is everything that's going on here. If we were just differentiating cosine of natural log, what would we do? Well, we would differentiate the outer function cosine to get negative sine. We'd keep our inner function exactly the same, so natural log x. And then we would take that inner function, the natural log x, and multiply by its derivative. So this is the second time we use the chain rule. So just another link in the chain. And if we had to do it again, we would just do it again. But in this case, we eventually get to something that we can just do. So going through everything here, we have cosine of natural log x times negative sine of natural log x. And then finally, that natural log x term, that's something we can just do. It's 1 over x. And to clean this up, I might put the 1 over x in front, and I might put the negative 1 with it. So if I were going to rewrite this, I might write this as negative 1 over x times cosine of natural log x times sine of natural log x. Again, not absolutely necessary to do that, but it's easy. If you leave negatives in the middle there, it's easy to lose track of them. So it's helpful to put sort of the smaller terms in front, just so you don't lose track of them. All right, so we can use the chain rule more than once, and you kind of see why it gets its name. It's just links in the chain. You just keep going, and you work your way through the function as you're differentiating. Let's try one more example like this. We're going to differentiate y equals e to the tan of 3 theta. And so when we look at this, it's an exponential function. And so the e, that's sort of our outer function. And then everything else, everything in the exponent there, that's really our inner function. So when we differentiate this, we're just going to use our general exponential rule. So we're going to get y prime is equal to. And how the general exponential rule works is you just keep the exponential part the same, exactly the same. So e to the tan of 3 theta. Keep that part exactly the same. It looks like we didn't do anything, but we did. Derivative of e to the x is just e to the x. So it's just because the exponential function really, you can't tell the difference when you do its derivative because it stays the same. And then we take the term that's in our exponent, the tan of 3 theta, and we multiply by its derivative. So this is the first time we're using the chain rule here. Now when we look at this, tan of 3 theta, really the 3 theta, I want to use a different color. That 3 theta now, if we just focus our attention on differentiating tan of 3 theta, that 3 theta is inside the tan function, and the tan, that's our outer function. So if we just focus in our attention on differentiating tan of 3 theta, tan is our new outer function, and 3 theta is our new inner function. So we're going to use another chain rule here to differentiate this. So to keep going. So we have e to the tan of 3 theta. That part we're done with. So we keep writing it, but we're done with that. Then we're going to multiply. And now we're applying the chain rule again. So what's the derivative of tangent? Go to our list, and we see that the derivative of tangent is secant squared. So we'll write this as secant squared, parentheses. And then inside our parentheses there, we write down the exact same inner function. We keep that part the same. So we differentiate tan to get secant squared, and then we plug in our inner function 3 theta. All right, now we take that inner function and then we multiply by its derivative. And so this is really what's going on here, this is really the second time we've applied the chain rule here. We differentiated tan to get secant squared, kept the 3 theta the same, and then multiplied by the derivative of our inner function, the derivative of 3 theta, and then we just keep going. So the e to the tan 3 theta we're done with. Then we have our secant squared times 3 theta. We're done with that. And if we differentiate 3 theta, we just get 3. And maybe it's helpful to just move that 3 and put it in front. If we wanted to rewrite this, again, not absolutely necessary, but it's easy to lose track of those little terms at the end. So it's usually helpful to put those in the front. All right. So chain rule, we can just kind of keep working our way through the function until eventually, just keep applying the chain rule until eventually we get to something that we can just do. Like in this case, 3 theta. All right. One more sort of alternative version of the chain rule. And it's more of a shorthand notation. So this alternative format says the derivative dy dx is equal to dy du times du dx. So this is more of a kind of a shorthand Leibniz notation type version of the chain rule. And we'll see where we would maybe use it in the next example. But let's just see where this comes from. So it really comes from just the original form of our chain rule that we've been looking at. And to see this, we're going to let y equals f of u of x. So we're interested in doing the derivative of f of u of x. That's what we're interested in doing. So we're just going to say that composite function, let's just call it y. Now, in order to make the notation a little simpler, a lot of times we shorten our notation here. So instead of writing u of x, we might just shorten this to u equals u of x. So we just call it u instead. And so another way to think of this function or this term y is to think of it with this shorter notation, f of u. So careful how you say that. So there's kind of two ways to think of y here. We can think of y as f with u of x plugged in, or we can think of y as just f with variable u plugged in. And so in the first case here, we're really thinking of y as a function of variable x. And in that second case, we're really thinking now of y as a function of u. So there's kind of two variable terms going on, x and u. So in the first case, in that longer version, we're thinking of y as a function of x. In the more condensed version, we're thinking of y as a function of u. Now, in each of these cases, it makes sense to talk about the derivative. So in the first framework here, we would talk about dy dx, and what that represents is it's the derivative of f of u of x. In the second sort of framework for or instance of y, when we talk about the derivative, what we're really talking about down here, if we're thinking of y as a function of u, when we think of the derivative, we're really talking about the derivative of y in terms of u. And so what this is f prime of u, which is really just f prime of u of x. So if we regard y as a function of x, then the derivative would be dy dx. If we're thinking of y as a function of some other variable u, when we talk about the derivative would be dy du. So if we look at what we have from our original chain rule, derivative of f of u of x, this is dy dx over here, this whole thing. And then our chain rule says this is equal to f prime of u of x. And that's exactly what we're seeing here. And we're seeing it down here. So that is dy du. And then finally, with this chain rule, we're multiplying by u prime. And so this term in the middle, u equal to u of x, that's a function of x. So it does make sense there to talk about the derivative. So if we talk about the derivative of u, we would be talking about the derivative of u in terms of x. And so here it's u prime of x. And so if we fill that in, u prime of x is just du dx. So this more shorthand version of the chain rule says the derivative of y in terms of x is equal to the derivative of y in terms of u times the derivative of u in terms of x. And that's what we're seeing down here. And so you get a little bit of the kind of why this is working out is because we're thinking of y as a function of x, and we're also thinking of y as a function of u. So it kind of has this dual nature almost. So let's see how an example of where we might use this alternative version of the chain rule. All right, so let's say we wanted to calculate the derivative dy dx, where y was given as a function of u, and then u was given as a function of x. So when we look at y, it says we're given y is equal to u squared, or u to the power 5 minus 2u cubed plus 8. So when we look at that, this is really y is a function of u. So as it's written, y is given as a function of u. Then we also have u over here, and we're told that u is equal to x squared plus 1. So this is telling us u is really a function of x. And so combining those, what it says is that really y is indirectly a function of x. So y is a function of u is a function of x. So if you kind of eliminate that middleman there, y must be indirectly a function of x as well. And so we're interested in talking about dy dx here. And so this is the derivative of y with respect to variable x. So we're really interested in how does y change, the change in y, as x changes. So x is the thing that's going to be changing here, and we want to see, well, how does y change as x changes? And so in this instance, we're going to use our chain rule because we see that it's kind of broken down into these two separate functions. So our chain rule says the derivative of y with respect to variable x is equal to the derivative of y with respect to variable u times the derivative of u with respect to variable x. All right, so how do we do this? Well, dy du, we're just going to do that derivative. So what's the derivative of y with respect to u? Well, we bring down the 5, keep our variable the same, u, and then subtract 1 in the exponent. Do the same thing for our next term. We get negative 6u squared. And then finally, the plus 8 is a constant, so that differentiates to just 0. So this is our derivative of y in terms of variable u. Now we want to multiply that with the derivative of u in terms of variable x. So our u term there is x squared plus 1. So when we differentiate u, we get 2x. And so this is our du dx term. Now that's not the end of the story here. Because we're talking about the derivative dy dx, we want all of our variables to be at x. And so the last thing we're going to do here is we're going to replace the u terms that we see with x's. So where do we see a u term? Well, we see it right here. And what we're going to replace that with is what we know u is, x squared plus 1. So we're going to write that first term as 5 times u squared plus 1 raised to the power 4. Then we subtract, we have 6. And then we're going to replace that u squared, or that u term, with an x squared plus 1. So we'll have x squared plus 1 squared, and then we still have that 2x on the outside. So in each of these cases, we replace the u, and I didn't replace it. Let's clean that up a little bit. That's a typo. So when we replace the u term, we're replacing it with x squared plus 1. So that u became an x squared plus 1. And just like this used to be a u, and we replaced it with x squared plus 1 as well. And so now we have a nice version of our formula for dy dx, all in terms of variable x, courtesy of our chain rule. All right. We got a few minutes. I think we'll stop there. I don't want to get into implicit differentiation. We'll get through like one page. So we'll stop there for today. So again, just a reminder for people with recitation today on Thursday, you're going to have your recitation exam. So make sure I sent out the Zoom link. So make sure you look for that in the email. You can also find it on our course calendar. And then we also have homework D1 due tonight. So make sure you finish that up as well. Not on the exam. D1 will be on the next exam, but just keep that in mind. The homework is due tonight. All right. So let's stop there. Good luck finishing studying for the exam, and then have a good weekend. And then we'll see everyone next week on Tuesday.